Okay, so my name is Shai 𝗠𝗏𝗄𝗧, and I'm the VP Data and Data Science here in Explorium. So I'll tell you a little bit about Explorium in the coming slides. But first of all, thank you very much for coming, and thank you for Nastya for giving the great talk. So as I promised, I will talk about Manifold, and it's a tool that was released and developed by the Uber's team, dealing with debugging machine learning models. I actually must admit that I, for a long time, planned to look at Manifold, and using this meetup, I thought it will be a good opportunity to dig deeper and to see what it's all about. And when I dug a little bit deeper in Manifold, I actually got a little bit disappointed. So I researched a little bit more, and I added a comparison to a different tool that I liked much better, but I will come to that. Credit when it's due. So all those projects are not mine. It's not an original work. So all the credit belongs to those people that developed those wonderful projects, and all our mistakes are mine. So if someone here hears something that sounds not accurate, raise their hand. It's OK. I won't take it personally. It's not mine. OK. So first, a few words about Explorium. So we are developing a data science platform focusing on the data part of data science. What does it mean? So like maybe many of you, or some of you, when I started dealing with data science, the ecosystem of the tools looked like that. And I know here that at least a few people were in the same boat. But as time passed, the ecosystem matured, and we developed a lot of tools, a lot of wonderful libraries and implementations. And the focus of what we are doing as data scientists, actually it wasn't called back then a data science, it's moved to different parts of the process. So while about 10 or 15 years ago, we were working with limited data, and a lot of focus was on the implementation of the algorithms. Today we have more data that we can swallow, and the models keep on coming. And the great thing about this ecosystem that it's very based on open source, so we keep on getting new toys literally every couple of weeks. And the focus shifted to using the right tools with the right data and understanding how to get the right things for the right problem. And that's exactly what we are focused on. So as I said, the data part of data science is where everything begins. Today, in the companies that are set their data science practice, usually those companies manage to organize their internal data pretty well, so they can facilitate really nice projects, building good models upon them. But as you all know, most of the data is out there, is outside of our organizations. And we know that, but getting it and understanding which data can be useful for us, it's actually a really hard task. So our focus is to broaden this beam and to get all the data that is available out there to our fingertips, and doing it in an algorithmic way. So what does it mean? It means that our platform is KPI driven. What I mean by that is that when data scientists are coming to use our platform, they better have some benchmark and some working model, and that they know what is the KPI that I want to optimize. And then our platform will analyze the training set, deducting what are the data that consist in these columns, and attach the right ontologies to those columns. Based on those ontologies, we can search through a big catalog of external data sources, whether open data sources, things like census data, various data sets of all the statistical bureaus of the different countries, or proprietary data that is being sold or we get by partnering with companies. So we can see which data can be matched to your training set. And from there, we have an automated machine learning pipeline training models with additional data to see where we can get the KPIs go up. And by that, we can find the data sources that actually can move the needle for you. So that's our task. we are focusing on the data side of data science, and it's really tied to the topic of today's lecture because we all know, we're well aware of this paradigm, garbage in, garbage out, right? So being able to understand how to analyze the results, understand where the problem lies and what is to blame and where we can do some changes to achieve results is exactly what we're trying to do because, as I said, we are driven by improving the end result and finding ways to open this black box and to understand who is responsible for what effect is a very hot topic, and it's an ongoing topic. So I start with, not with Manifold, but with Gamete as a project that was led by Microsoft, but actually it was a collaboration of various different universities. And what really caught me in this project is that those guys did problem formulation work. So they actually developed a tool, but that's not a focus. They brought a bunch of data scientists from various backgrounds and various experiences, and they actually did a quantitative study to understand what data scientists are looking for when they're trying to understand the model, when they're trying to debug a model. So they actually gave them a problem. This problem specifically was related to, if I'm not mistaken, house pricing. And they, first of all, looked what questions they are going to try to answer. And those questions were aimed to formulate the vision, how the perfect tool will actually help the data scientists, what questions it should facilitate answering. So the first question was, for the pricing model, why does this house cost that much? Okay, so we enter a house, we get some price, why? The second was, what's the difference between those two houses? So we have one house priced more than the other. Why? The third type of question was that what if we add some modification to this house? So we have a certain house. If we will expand it with one more room, do some 𝗪𝗪 project, how it will add to the value of the house. And the next question was, what are the similar houses in our data set? So what makes houses similar for this model? And the last one, and maybe the most curious for some of us, is where is the model is getting it wrong? Where is the model is not pricing the houses according to their true price? So those were, I missed one. And what is the most important factor for pricing a house? So those questions actually were the questions that raised from this study group. They were translated and formulated into capabilities that a model debugging tool should answer. So the question, why does this house cost that much, was translated to local instance explanation. So being able to pinpoint an instance and to explain what exactly caused specific prediction of this instance to be as it is. What's the difference between the houses was translated into instance explanation comparison, comparing two instances and asking the question why. Why are they different? What if translated to counterfactuals? So the question is, I have a certain data point, but what if I change some parameters? What will it make to the prediction? What effect it will cause? Similar houses translated to nearest neighbors for the points. Where the model is getting wrong is all the area of error analysis. And what is most important is translated to feature importance. So those are the capabilities.
What about data that the model hasn't seen yet? I mean, you have the model, then you wanted to perform the same when you use it in the wild, right?
Sure. So actually, all this applies both to the model, the data that we model, that we learn on, but actually probably more interesting on the data that we don't see yet. So as we will see, those tools that were covered here are agnostic to the data that we feed them, but actually, as a data scientist, probably the most interesting aspects will be to see how it performs on the new data. Thanks for the question. OK, so as they wrote a paper, and they actually cover in details all the process and the results. And using that, they developed a tool, and they let those data scientists to play with it. And they actually saw where the different types of data scientists spend the most time in. So to make it very high level, and actually, if you want the details, go read the paper. I won't do them justice by giving them, explaining it in 20 seconds. We saw that on the side of local explanations, understanding how a price of a single instance is combined, most of the focus was for the novice data scientists. The more experienced data scientists spent more time looking at the features and specifically on the dependency plots of each feature, so to understand how each feature influences the model if the instance is, the value of this feature is changed. But the most experienced data scientists actually did this, their work by combining, going between the local and the global areas. The sad thing about it is that they didn't release this tool, but actually it was not the promise. As I said, the whole focus of their work was to formulate the problem, and I think they did a really good job. And that caused me to actually, now we are equipped with criteria to analyze the tools that I actually wanted to talk about. So we can say that we see that understanding the performance of the model is just one point there. It gets a lot of attention, and a lot of time when we're talking about how the model performs, we are talking about the various matrices: classification accuracy, precision recall, AUC. But as probably most of you that you are using that and trying to push the real model into real production systems know that once you get some score, you have a lot of additional questions. OK, now what? And then make us move to a different domain of questions, answering the question how our model might perform, how it might perform on new data, how it might perform on different subsets of data, how it might perform on the different, how the different differences in models can influence the matrices, etc. OK, so finally we got to Manifold. So as I said, tool created by Uber's machine learning team under their 𝗵𝗶 It's their great machine learning platform project. They also wrote a paper about it. Actually, there are discrepancies, or at least some things that are mentioned in the paper that didn't implement in the project. And I don't know, maybe they implemented internally, but not in what they exposed or released outside. What I really liked about the way they approach it is this formulation of moving from the model space into a data space. So understanding that to understand how the model performs, we need to look how it performs on the data and analyze it from there. OK, so the three main parts of Manifold workflow is being able to compare, performance, and I'll get in more details into each one of them, to slice the data sets into interesting groups, and then to attribute the differences to various features. By the way, Nastya, I welcome you to give some comments about application of the right principles in their visualizations. OK, so the way it works, what we feed into the tool, to the Manifold, is a predictions of each of our models. It can receive one prediction of one model or several models, and some ground truth vector. Gershon, it's for you. And in the end, what we get is some performance metrics. So it can be a log loss or any other metric that combine the prediction on different classes to one metric. And the next thing, and I think that's the original part here, is that those predictions are being clustered automatically into segments that behave the same in the prediction space. So what we can see here is that, and this tool is have a visual interface, is that once you change the number of clusters, the system is automatically grouping them into similar sub-segments. And then what we can do on those segments is to visualize and compare the difference between the models. So what we have here is red and green are two models that we are comparing. This x-axis is the log loss, so lower log is better performance. And we have 4 clusters here that we see that behaves differently. So this plot is a violin plot. How many of you are not familiar with the violin plot? OK, great. So it's a density plot, a count plot. So we can see how many instances we have in each of those points. So if the weight is big, so we have many instances, and where it's very low, we have a little. The x is the median, and then we have the percentiles, 25 and 75 percentile. And what we can see here is that in one cluster that have a big chunk of the data points, the deep learning model is performing better than the XGBoost-based model. But we see that there are other clusters that the behavior is the opposite. And then we can deep dive and analyze what exactly is going on there. OK, so that's the second part, the feature attribution part. So we can take a segment, a group, and to analyze the features that are the most different between the two segments. So they are being ranked by the difference, by KL divergence between them. And what we can see here is a histogram of each feature. So for the first feature, the red line showing the histogram of the value of this feature for some segment, and the brown line for the control group. So we can see that for the treatment and control, for the treatment group, we have in feature name 0, we have more lower values. And for the control group, we have more higher values in the 0 feature. And we can see that the first 3 features are different, but as we go down, they behave pretty much the same. So if there is a difference in performance, it's probably attributed to the first 3 features. So that is allowing us to do this iterative analysis and our data into similar different segments and to compare them. And as you can see here, we can group those clusters into segments that we want to analyze together. OK, so actually, the workflow is combining those 2 panels side by side. And as you can see this in the demonstration, once you update something on the screen, so it's automatically recalculate and update everything else. And the last part that I mentioned, that we have some kind of filter helping us to find the more different features. OK, so one technical bit before I'll go to some example. They actually went and implement everything in the client side to make it agnostic to the background. And they did a pretty impressive work using TensorFlow.js, making all the computations using WebGL, so using very efficient graphical frameworks. So they managed to make it everything run in the browser and achieve sub-second latency on those calculations. OK, so the use case here is to find to analyze what happened with some new features that they added. So their example is that they trained the model. It didn't seem a very significant performance improvement, even though they felt that those features should help. So they analyzed, compared those two models, and they saw that there is actually an improvement, but in very small section, but it's a very hard one. Okay. A second example of the use of this platform is understanding how to eliminate false negatives. So here, the first step was to cluster the points and to find the points that are falling above some decision threshold. It's a binary classification problem of a safety team in Uber. So we see that all those points are below this line are the treatment, and the control is those that are above the line, that are true positive. Now when they compare those two groups and saw that the first four features actually behave differently, they see that this feature A, B, and C are getting lower grades versus their counterparts of the true positives. And then they compare it to a different segmentation, taking into account all the population. And here, the different colors are the negative group and the positive group. So they actually could explain it and to see that things that got false negative actually correlate with, those features are correlate with the fact that the negative class is getting lower scores in those features. So I guess here they didn't do a really good work from the Gestalt principles, because everything seems pretty much the same. But reading into it, it kind of makes sense when you read what exactly they meant by that. And the last thing that I want to mention about Manifold is that once they released it, they added a support to run it outside of their platform and not using only the web app, but to integrate it with Jupyter Notebook. Basically, what you are getting is a JavaScript version of it running in the browser, in the network. As I said, not super intuitive from my impression. And the part that I was missing the most is the fact that even though they talked about moving to the data domain, they didn't actually provide any way to touch the actual data, to go to a specific sample and to see what's the difference there. So just a very fast recap. We can feed results of various models. Manifold cluster them into groups. Those groups can be arranged into segments, and segments can be analyzed side by side. And those outcomes can be translated into a treatment for features. Yeah.
Can you manually cluster yourself in those subsets by yourself?
So actually, it's a great question for them, because they just added it when they released it. Like if I compare it to the first version that they talked about, they added the version that you can skip the clustering and you can define the segments by yourself.
Does it support also regression models, or only
Yeah, it also supports regression models. Actually, there's nothing here that ties you into a classification problem.
Is there some specifics for NLP problems of image recognition problems?
I didn't see that. I didn't see support for NLP problems. I did saw that they added some visualizations for geographical data, but in the visualization level. Yeah.
So if I understand correctly,
Yeah.
they have to have separate features. So I'm not sure if it's suitable for deep learning.
That's a good question. I don't know how they tackle that. It seems that they aim it to a more classical models, even though they mentioned deep learning there. I guess you could feed some internal representations and to analyze those levels.
It sounds like it more fits to classical problems, but what about sequence input or image inputs? Does it have any solution for these use cases?
So I didn't see that explicitly mentioned. As I said, the framework is pretty generic, so I guess you can feed the problem in a way that can translate to features and performance and use it this way, but I didn't see anything specifically fitted to this specific problem. How am I with the time? 10 more minutes. Actually, I would like to cover one more thing quickly, and maybe I'll take more questions there. So they're actually an online version that you can just log in, play with, upload your data, and get your own impression. While researching about if there is something better than that, I actually tackled into Google's Paralab What If tool. How many of you are familiar with it? Okay, great. It's because it's amazing, and I was also surprised to discover it and the fact that I was not aware of it before. They also released a paper. It's relatively new. And they tried to tackle a very similar goal. So since we have only 10 minutes, I'll just go with giving you some intro about what it can do. So their goal was similar, to create a minimal coding environment to analyze data sets. It also runs in a browser. It can integrate, and actually it probably was part of the TFX, so it integrates really, really well with TensorBoard, but it also can be run from within a notebook. And I will go with some example of a data set and a problem. It's a pretty famous one. It's a UCI data set of census data, trying to predict the persons that will have a high income. High income is defined by more than 50K a year. So first of all, what you can do, and this part of the tool is a part of the project called Facets, I think, Facets Dive. So that gives you a lot of options to visualize the data. Each point here, it's a prediction point and a point from the data set. And first of all, when you scatter the points, so we see that many of them are getting the extreme values. Blue ones are high income, red ones are low, and that's the probability to get high or low. So we see that our model have some extreme confidence in the edges. What we can do by adding some scatter on the x-axis, which is, in this case, years of education, we can see that we start to see some patterns. So the more years of education, the higher the chances that the person will have a high income. An additional feature that they have is binning. Okay, so adding a binning by marital status can give us a breakdown by this additional parameter. So what we see here is that most of our data is in married with a spouse. And we see that in this bracket, the data is pretty balanced between high income and low income. We see that we have much less data in the other brackets, and it tends to the lower income. An ability to add an additional breakdown. So here, what we are binning by hours of work per week, and we add the color aspect, giving us the marital status as a color. Show us a picture of the majority of the people. By the way, the data is from 1984, so it might be changed. Sorry, 1948. So maybe the pattern was changed by now. But we see that most of the people tend to work between 31 and 40 hours. Some people reported working 99 hours a week. We can see, I don't know if it's influenced their divorced, right. We can do it in two dimensions. We can do a kind of two-dimensional histogram. So we added this marital status as a binning on the y-axis. And then we can see some different trends. So we can see that if you look at the never married, we can see that this bracket is going down with the age. One additional interesting feature that they have, except of just plotting the data, is actually touching the point. So clicking on one of those points will give us the exact details of this data point, and will allow us to play with it. So we can see how this point is predicted by two different models. We can change the point and see what will happen if we change this value. We can find its nearest counterfactual. So the point that is closest but getting the other prediction. Okay, so we can define how exactly we want it. And we will get the nearest point, and we see that only the age is pretty much different, but and the occupation, but pretty much all the rest is the same, and the outcome is very different. Another thing that we can do, we can sort all the points by closeness to the point of interest that we chose. So we see that the closest counterpart is here, and all those points are sorted by how they close or different from the point of interest. An additional thing we can do with this tool, actually there are probably infinite number of things, but I picked the one that seems more interesting for me, is to plot the scores of two models, one against the other. And then we can examine what's happening in the decision boundary to look what are those points that are being scored in some way by one of the models and different by the other. Now, an additional thing that they provide is an ability to analyze the features using a partial dependency plots. So we can do it both on a point level to see for a specific point how, if the age was, the feature of age was changing, how the outcome will change. And here we see in pale line is the threshold for this point. So we can see that it's a pretty linear relations for age, for example. On the here, when we have discrete parameters, so we can see it as an histogram. And we can see that, again, the higher degrees, the more chances to earn more money. There is a view giving a deeper dive on the whole feature set, providing some statistics like basic statistics, but also zeros and histograms. We can see that, for example, male and female are not represented in the same way in this data set, and we can see that when we look at the capital gain or loss, I think I actually have a better slide here. So it's not even redistributed. So we either have people that have no capital gains at all, or most of them don't have it at all. And of course, we can drill down and see all the details of how many different categories we have in categorical features. So we see that this dataset is mostly combined from United States citizens. Now the last part is the model analysis part. So there is a very nice tool to analyze the different thresholds and to analyze the confusion matrix. They provide the ROC score and precision recall score, plots. We can do it on several models together. So we can analyze how they behave with same threshold, or we can optimize for some false positive, false negative loss. And we can actually do an additional analysis using, when this information is available, to check things like equality and demographic parity. So we can see how the model behaves on male and female, and to see if the behavior is discriminating some group. And the last thing is the fact that, and I think that ties to your question about different data types. So it's very highly customizable. So they provide a lot of support for various data types, including pictures, and actually have way to customize pretty much every aspect of the tool. So you're welcome to go into their website and play it with it by yourself. And thank you. So actually, my question to you is, are you using what are the tools that are you using for those problems? And if someone has some interesting tool that the others should know about, please share. Elena, it sounds like you have some idea.
Hi. Tomorrow I'm going to use it because I compare, like, we got two models, and at the beginning, one model was much better, and now suddenly I tried it on another set, and like so many false negatives. So I'm going to look at it, or maybe I will try this. What do you think is best for me?
So I think like 𝗨5, it's a wrapper around tools like 𝗨𝗯𝗲 and 𝗁, which are giving prediction, local prediction explanation. And I think that, I mean, I'll take it back. It depends exactly which plot in the 𝗁. But I think those tools can be combined because what 𝗨𝗲 and 𝗁 can give you is, I think it's very different than looking at your data set and seeing what is, how each group there is represented. So I think that analyzing the group of the false negatives here and looking what make them close together, what are the counterfactuals that are making them confusing, it might be interesting. Any additional remarks, questions?
We use bokeh dashboard just to merge all our visualization website, and we can actually add what if tool just as another window to check whatever you want. Just the fact that all your visualization are in one website makes it really powerful.
Thanks for sharing that. Any more comments, questions, remarks? So, thank you very much. Oh, I forgot the most important slide. We are hiring. We have positions for various roles, but also various roles in the data science organization. So those of you who are interested, so first of all, take a picture, but then you also can go into our website or directly speak with me. My email is Shai@Explorium, and you're all welcome to be in touch.